Hi, I'm Rowan from Vantage Admissions. In all my years of working with students preparing for the TMUA, one of the recurring themes has been that questions using necessary and sufficient conditions cause a lot of trouble. Indeed, these problems are a real hallmark of Paper 2 of the TMUA. In this video, we're going to give a very brief overview of what we really mean when we talk about necessary and sufficient conditions. And we'll also think about the best way to conceptualise these ideas, specifically when dealing with TMUA problems. Towards the end, we'll also look at some original examples demonstrating these useful ways of thinking. Let's begin with sufficient conditions, which are generally found to be a little easier, since it essentially means the same thing as in everyday language. The word sufficient in mathematics means exactly the same as in everyday language. It just means enough. So if we say that A is a sufficient condition for B, or A is sufficient for B, we're saying that if we know A is true, that is enough to guarantee that B is also true. In other words, in the language of implication, A implies B, so we'll often depict this with an implication arrow. Now, this is exactly the same as saying if A, then B, or B if A. So an important point we'll see today is that necessary and sufficient is exactly the same thing as if and only if. So if is the same as sufficient. So let's think about some examples. So f of x is a cubic is clearly sufficient for f of x equals 0 has at least one real solution. Because if you think about the shape of a cubic, whether it's a positive or a negative cubic, every cubic will cut the x-axis at one point. X is a pot-bellied pig is sufficient for X is a mammal, because if I know that a given organism is a Vietnamese pot-bellied pig, certainly it has to be a mammal, because a Vietnamese pot-bellied pig is a type of mammal. Or a quadratic q of x has a positive discriminant is sufficient for the quadratic to have two real solutions. Because we know it's a fact that when we do have a positive discriminant, that does guarantee the existence of two solutions given by the quadratic formula. Notice that, for example, the discriminant being positive is not sufficient for two integer solutions. Although it's entirely possible that by coincidence our solutions might be integers, this is certainly not guaranteed. Necessary conditions can be a bit more challenging, and it's very easy to confuse yourself about precisely what the claimed implication is. When we say that A is necessary for B, we're saying that A is needed to have any chance of B being true. Now, it's really important to remember that we're not suggesting that A being true guarantees B is true. We're just saying that it's needed if you're going to have any chance at all of B being true. So in other words, if you don't have A, you've definitely not got B. Sometimes this is phrased as only if, so A necessary for B is sometimes phrased as B only if A. But it's really important to be careful here. This does not mean the same as what it would in everyday language. So consider the following conversation between Alice and her teacher, Mr. Bob. So if Alice says to Mr. Bob, "Will I do well in the TMUA?" And Mr. Bob says to Alice, "Only if you study hard." As an everyday language conversation, an entirely reasonable inference from this conversation is that not only is Mr. Bob saying, you definitely do need to study hard if you're going to do well, that's needed if you're going to do well, you may also reasonably infer that he is implying, yeah, sure, if you study hard, you will do well. But in mathematics, when we say only if, there is no implication of sufficiency. So Mr. Bob's statement in mathematics is not stating that if she does study hard, she will do well. It's only stating that if she doesn't study hard, she won't do well. So it's a really important point that this is one of the rare instances where the meaning in logic is slightly different from what the meaning would often be taken as in everyday language, where of course we're generally less precise with what we mean. So in terms of an implication, I would say that the naturalist way to infer an implication from A necessary for B is actually not A implies not B. So the implication doesn't come from A, because if A is a necessary condition, as I've hopefully really emphasized in this particular section, knowing that A is true does not necessarily tell me B is true. If A is necessary, it's only the case that not having A guarantees that I don't have B, because I needed it to have a chance of B. So the most natural inference is not A implies not B. Now you'll often see in textbooks and notes that they will phrase A necessary for B as B implies A. So they'll have the implication coming from B and running to A. Now, this is completely equivalent to the form I gave, not A implies not B. In fact, it's just the contrapositive of it. So although it's not the focus of this video, we have the idea from logic that if I take a statement and I negate both parts and I reverse the direction, so I turn not A into A, I turn not B into B, and I reverse the direction, so it now points from the B end to the A end, that's called the contrapositive of a statement, and it's logically equivalent to the original. So that's why we can say, well, it reads B implies A. Now, this does make sense. If A is needed to have a chance of B, then if you do have B, you must have had A. But I would say that in many cases, the not A implies not B formulation is actually more intuitive, easier to work with, and helps avoid the trap of incorrectly inferring that A leads to a conclusion. Ultimately, for TMUA, we should be fluent with both. So thinking about a few examples, X is a mammal is necessary for X is human, because a human is a type of mammal. So if X were not a mammal, there's no chance that X could possibly be a human. But it's not sufficient, because it's possible that X is a non-human mammal. X might be a capybara, for example. So it's not enough to guarantee that X is human, but it is needed to have any chance of X being human. Another example, quadratic Q has positive discriminant is necessary for two real roots, because based on our classification of the number of roots of a quadratic according to the discriminant, we do know that without a positive discriminant, there's no way we could possibly have two real roots. And in this case, it's also sufficient, because it is the case that knowing a positive discriminant does guarantee two real roots. So sometimes things can be necessary and sufficient, or necessary but not sufficient, or sufficient but not necessary. These are logically independent things, so you have to study each individually. Let's now take a moment to think about how necessary and sufficient conditions relate to each other. So we've already observed that when we say A is sufficient for B, as an implication, this is the statement that A implies B. Similarly, if A is necessary for B, via our contrapositive version of the implication, we know that this is saying that B implies A. So you'll notice that when I've changed the word sufficient and the word necessary, all I've done is I've switched the direction of the arrow between A and B. So a nice consequence of this is that saying A is sufficient for B is the same as saying B is necessary for A, because by changing the word sufficient to necessary, I've swapped the direction, but if I also swap A and B over in the statement, as I've done here, well, I've swapped twice, so I'm back to where I started. So A sufficient for B is the same as B necessary for A, and similarly, A necessary for B is the same as B sufficient for A. So if you find yourself confused about a given statement, you can always change it in this way. You can change a sufficient statement to a necessary one, or a necessary one to a sufficient one, to see if that helps you to think more clearly about what's going on. If we have both necessary and sufficient, A and B both imply each other. This is what we sometimes say if and only if. It's exactly the same thing. But if A and B imply each other, it means they're completely logically equivalent. They're either both true or they're both false. So in this way, we can think of them as being sort of different ways of saying the same thing. And it must be emphasized again that something might be both necessary and sufficient, it might be neither, or you might have one but not the other. So we need to assess each direction individually. Having pinned down precisely what we mean by necessary and sufficient conditions, how should we think about these ideas in the context of TMUA questions? where we're likely to be dealing with challenging mathematical contexts and are also very pressed for time. Rather than trying to think about everything in terms of implications and constructing direct proofs, the vast majority of time in the TMUA, the best way to think about necessity and sufficiency is in terms of counterexamples. So the first thing you need to do is think really concretely about what a counterexample would actually need to do. Put it into words, even write it down if it helps you to think about what's going on. So if I had a counterexample to A being sufficient for B, I would need a case where A holds but B does not. That's what shouldn't be possible if A was sufficient, because if A was sufficient, A would guarantee B. Similarly, if I want a counterexample to A being necessary for B, that would be a case where I don't have A, but I do have B. Because again, that's what shouldn't be possible. I should need A to have any chance of B. And if I have a case where I don't have A, but I still do have B, that's a counterexample which would disprove necessity. So after having identified very concretely in the context of the particular maths you're dealing with what a counterexample would do, you should then either be able to find a counterexample, use the usual techniques, try simple cases, try extreme cases. You'll generally be able to find a counterexample quite easily if one exists. Or alternatively, once you've put into simple terms what a counterexample would actually look like, you might be able to see or convince yourself that one simply can't exist, in which case the condition really is sufficient or necessary. So although counterexamples are in some sense a different topic from necessary and sufficient conditions, they are usually the right way to center your thinking in these problems. A direct proof, a deductive proof, actually writing a proof that, say, A implies B, will very rarely be necessary. And in most cases, even if you are going to do that to convince yourself, you can be guided in any case by counterexamples, because your consideration of what a counterexample would look like will give you some intuition for why a counterexample can't exist, and therefore why the implication has to hold. So counterexamples are our best friend in these problems. Let's now work through a couple of examples in the style of TMUA problems. Rest assured, these are not real past paper questions, but they're original exercises which we've devised, so you don't need to worry about spoiling any of the past papers. So in this example question, which forms part of one of the papers, the extra papers we give students on our programme, we're considering the functions f of x is log base 2 of sine of x, and g of x is mx plus c, where m and c are real constants. We need to decide which of the following statements is or are true. So we have an if and only if, so that's of course the same as necessary and sufficient. We have an only if, which of course is the same as necessary, and we have an if, which of course is the same as sufficient. So essentially all of these claims are talking about the number of solutions to the equation, which really means the number of intersections between an arbitrary straight line, so mx plus c is just some straight line, and the graph f of x equals log base 2 sine of x. So as ever on a TMUA problem, we're centering graphical reasoning. Let's try to draw the function of f, the graph of f that is. Once we've drawn the graph of f, we can think about, for different types of straight lines in relation to these conditions, what we can say about the number of intersections. So the graph might be a little bit tricky, but once we have the graph to hand, it should be very easy to think about counterexamples. And let me also emphasize, when we come up with counterexamples, say, we don't necessarily need to actually write down a value of m and c. Because I know that as m and c vary, I'm basically able to pick up any straight line I like. Drawing a counterexample is enough to convince ourselves. So it's often easier to give graphical counterexamples than explicit functional counterexamples. So let's think about this function. First of all, it's clearly going to be periodic with period 2 pi. Because if I change x by 2 pi, I know sine has that symmetry. So if I shift x to x plus 2 pi, the sign has not changed. But if the sign has not changed, then the thing being eaten by the log has not changed, so the output doesn't change. So we inherit the periodicity. So if I just sketch this thing for 0 to 2 pi, I can generate all the rest simply using periodic symmetry. Now, when x is 0, what have I got? Well, I've got log base 2 of 0. That's not actually allowed, right? You can't actually put 0 into a logarithm. But if I put a tiny positive number in, as will be the case if x is a tiny positive number, then we know that, the log graph will look like this. We're actually tending to minus infinity. So I can see straight away that near x equals 0, I've got a vertical asymptote because I've got log base 2 of something really tiny. Okay, now, as x varies from 0 to pi by 2, sine is going to increase. So it's going to increase from 0 up to 1. Now, when I feed a logarithm a number between 0 and 1, I'm going to get something negative until I actually put 1 in, at which point I'm going to get 0 out because, log base 2 of 1 is actually 0. So I know that by pi by 2, I've increased up to a value of 0. Now, the graph flattens here because sine flattens at pi by 2, right? Sine is going to look like this. So if the thing going into the log is flat, the change in the function is going to be flat as well. You don't need to use the chain rule or anything to see that. And then clearly, as I increase x from pi by 2 to pi, just like from here to here, the sine went from 0 to 1, I now go from 1 back down to 0 in an exactly symmetric fashion because the sine function is symmetric about that peak. So I'm going to do the same thing just in reverse, and I'm going to have another vertical asymptote at pi, because by pi, I know that I'm now getting 0 from the sine again. Right, now, when x is between pi and 2 pi, the sine function is actually negative. I can't put a negative number into the logarithm, which means that until 2 pi, the graph is nice and easy to draw. We just leave it blank. There is no graph, right? There is not a real output because we're putting something negative into a log. So there's this nice shape from 0 to pi. There's nothing from pi to 2 pi. And then we're just going to continue in this way. So we don't need to draw this as a sort of real work of art, just a very rough outline of what we've got. So we've got all these negative bits, and it just continues with these gaps in between. So that's nice and easy. Now we can go through the statements and try to think about counterexamples. So statement 1 says we have infinitely many real solutions only if m is not 0. So if m is not 0, or if and only if m is not 0, m is not 0 means the straight line is not flat, it's not a horizontal line. So what would a counterexample be? Well, because this is if and only if, there's really two statements being made at once. There's the if and the only if. A counterexample to either would rule one out. So one form of a counterexample would be if I had that m was 0, so this didn't hold, but even though I had m being 0, I did have infinitely many solutions. So that would be a contradiction to the only if. Only if is saying that m not 0 is required if I have any chance of infinitely many solutions. So if I had a case where I did have infinitely many solutions without m not 0, so with m being 0, that would be a counterexample to the only if. Alternatively, I could have a case where I had m not 0, but I actually only had finitely many solutions. So that would be a contradiction to the if, a counterexample to the if, because the if is saying, if I have m is not 0, I am guaranteed infinitely many solutions. So if I can find a case where my graph is not flat, I don't have 0m, but I actually only have finitely many solutions, that would contradict the if. Now it's very easy to find a counterexample to the only if. So m equals 0, a flat line which cuts infinitely many times. So I can simply draw a horizontal line at a negative value like this here, right? So this line clearly has m equals 0 because it's horizontal, 0 gradient, but it clearly does have infinitely many solutions. Remember, the graph is periodic. So although I've only drawn, a couple of periods, this pattern for the graph continues over this way and this way as well. So I'm going to cut every one of these little end shapes with that line. So really easy to see a counterexample to the only if, therefore statement 1 is not true. And because it's an if and only if, Once we've punched a hole in either of them, the whole statement's wrong, so we don't even need to worry about if. Okay, what about statement 2? So statement 2 says that there are no real solutions only if C is bigger than 1. So we're saying that unless we have C bigger than 1, there's no chance of having no real solutions. So again, let's be really concrete. What would a counterexample look like? Well, if we didn't have the necessary condition, if I actually had that C was less than or equal to 1, but I still had no solutions, right? Because I'm saying in this statement, unless I've got this, there's no chance of no real solution. So if I can find a case where I don't have that, but I still have no real solutions, well, that proves the statement wrong. But it's very easy to draw such an example. So again, sticking with simple examples to try to find them more straightforwardly, I can just use another horizontal line, right? So if I take, for example, m equals 0 and I don't know, c equals 0.1 or something, clearly that does obey that c is less than or equal to 1, but there's no real solutions, clearly, because this line only ever takes a positive value. And yet my graph of f is only negative, or briefly, 0. So we state really clearly to ourselves what a counterexample exactly would have to do, and then it should be pretty easy to see, oh yeah, I can find one, or alternatively, well actually one can't exist. Statement 3 is perhaps more subtle. So we say that MC being 0 implies, guarantees infinitely many solutions. Now what does MC being 0 really mean? Well, it means that M is 0, or C is 0, or both. So in maths, when we say or, we always have the inclusive or, we include the possibility of both. But if M and C multiply to give 0, then we're saying at least one of them is 0. So the claim is that M being 0 guarantees, well, if I know that either M is 0 or C is 0, that guarantees infinitely many solutions. But actually, this is already a counterexample, because MC being 0 could be satisfied because I had that M was 0. But if it were M being 0 that made that true, it's certainly not the case that we have necessarily infinitely many solutions. Because here's an example where we had M being 0 but not. So it's possible to have a case where MC is 0 because M is 0, but we don't have infinitely many solutions. So we have a counterexample to this as well, and so none of the statements are true. Let's consider another example. So in this problem, we're thinking about two sequences, A and B, which consist solely of positive integers. And we define the third sequence as A of B of n. So in other words, to find the nth term of the sequence C, you take the nth term of the sequence B, and that tells you which term in the sequence A to look at. So for example, if the fifth term in B is an 11, then the fifth term in C is A11, so you look at the 11th term in the A sequence. Now we consider the statement, C is a periodic sequence with some period, so of course that means if I go ahead by k in the sequence, I always get the same number. We're going to consider the following necessary and sufficient conditions. So let's again think in terms of counterexamples. First of all, for statement 1, which says that it's sufficient that B is periodic, what would a counterexample look like? So a counterexample would be a case where we have a periodic B, but C is then not periodic. Now that sounds implausible to me, because if B has a certain period, when I jump ahead, let's say it's period 5, if I jump ahead by 5 in the B sequence, I get the same thing out. But if I get the same thing out of the B sequence, I'm looking at the same term in the A sequence, so I have to get the same thing again. So once we've put it concretely what a counterexample would have to do, it feels pretty obvious this can't happen, that in fact the period of B is going to be inherited by C. If in any doubt, let's try to prove this. So let's say B has period K, for example. So remember, if I'm trying to show this is a sufficient condition, I want to show that this implies the statement. So if B has period K, that means that B of n plus K is the same as B of n. Whatever n is, if I go ahead by the period, I get the same thing out. But then my claim was that it's kind of obvious that if I then go ahead by K and C, I'm going to get the same thing again. Well, C of n plus K is A of B of n plus K, right? That's what C is. It's A of B. But B of n plus k is just B of n, that's what we said. And what is A of B of n? It's the same as C of n. So that means that C of n is clearly also periodic. Okay, so we see, firstly, by just realizing through sort of making clear what a counterexample would be, and then even with a deductive proof, clearly B being periodic does guarantee that C is. So this statement is true. What about statement 2? So statement 2 says that B being periodic is necessary. So we're saying that if you don't have B being periodic, you definitely can't have C being periodic. So what would a counterexample to that look like? It would be a case where B is not periodic, but C is. Surely that's possible. For example, surely if A is periodic, it's possible that C gets to be periodic as well. But what's the simplest example we can think of a non-periodic B? Well, what if I just let B be 1, 2, 3, 4, right? Just the integers. There's nothing wrong with taking simple counterexamples. They're often the most instructive. Well, if I let B just be 1, 2, 3, 4 and so on, that means that the C sequence is the same as the A sequence. So then, if I choose B in that way, C is going to be periodic, actually for any periodic A. So here's a counterexample. If I choose this as my B, that's not periodic. As long as A is periodic, then C will be. So I can clearly see it's possible to have B not periodic, but C periodic. So this cannot be necessary. Okay. The next option, 3, says it's sufficient that A is periodic. So that means that A being periodic guarantees the periodicity of C. So what would a counterexample look like for this? Well, it would be a case where we have a periodic A, but then a non-periodic C, right? Because that shouldn't be possible if A being periodic guarantees that C is. Now, it kind of feels like such a counterexample must be findable, because even if A is periodic, by doing something wacky with B, I can clearly make sure that I'm scrambling it up and taking all the wrong terms. So you might even be happy just from that sort of heuristic reasoning to say, yep, sure, 3 is not true. Clearly this counterexample can exist. But if we want to convince ourselves, let's try to construct one. So let's start with a really simple periodic A. We might as well go 10, 11, 10, 11, 10, 11, 10, 11. So that's periodic, period 2. Now, if I make a choice for the B sequence that makes sure I'm picking these terms out in a kind of scrambled way that gives a non-periodic output, that's a counterexample. So what if, for example, I say I'm going to take 1, then 2, then 2 1s, then a 2, then 3 1s, then a 2, then 4 1s, then a 2. So I'm writing a kind of pattern so that it's easy to be concrete about what the example is, but it's not periodic because I'm increasing the block of 1s each time. So I'm just trying to think of simple examples, because if I do that, then when I build the sequence C, well, first of all, I take the first term of A. Then I take the second. Now I take 2 of the first. Now I take the second. Now I take 3 of the first. Now I take the second, and so on. And this is clearly not periodic, right? So there are many, many examples you could write down. This is just one simple case I've gone for. But it's clearly possible, even if A is periodic, for B to ruin the periodicity of C. So by counterexample, statement 3 is not true. And then finally, statement 4 says that it's necessary that A is periodic. So a counterexample to this would be a case with A not being periodic, but C being periodic, because we're saying that you need A to be periodic to have any chance. But hang on a minute, we already have a counterexample to this. Any periodic B, we've already reasoned in part 1, if B is periodic, we definitely know that C is periodic, regardless of any condition on A. So A cannot possibly be necessary because we've seen that you certainly can have this happen. If I choose B to be periodic and A to be some non-periodic sequence, C will still be periodic. So, I mean, there's also an interesting point here that when we do these problems considering the same mathematical context, you might be able to use earlier examples, or you might be able to use earlier deductions, like that B being periodic implies C is, in order to make the later considerations a little bit easier and to save some time. I hope you found this lightning-fast introduction to necessary and sufficient conditions helpful. These are fiddly ideas that take time to build familiarity with, and you'll get lots of practice as you work through TMUA Paper 2. As a rule, for the more recent papers, you'll find that these concepts feature even more prominently. If you're interested in more structured support with your TMUA preparation, do visit our website where you can learn about the course we offer. Moreover, if you're interested in more videos exploring ideas from the TMUA and related admissions tests, do remember to subscribe. And thanks for watching.